Good morning, everyone. Today, the topic is basics of CT. And by the way, my name is Pandamina. I'm working as a technical assistant in Sri Chitrathirana Institute of Medical Science and Technology. To begin with, computer tomography combines both X-ray and radiation detectors, coupled with the computer to create a cross-sectional image of any part of a body. And the word tomography comes from a Greek word where tomo means slice and graphy is to describe. Both combines like we are describing a slice by slice anatomy of a body. And the history of computer tomography is like it was invented by Sir Godfrey Hounsfield Unit and Alan Cormack in 1972. The basic principle behind the CT is like internal structure of an object can be reconstructed from multiple projections of the body, and also it is like measured in linear coefficient of our tissues. And how is it measured? The average linear attenuation coefficient between the tube and detectors. And attenuation coefficient reflects on the degree to which X-ray intensity is reduced by the body. And why do we need to go for CT when X-ray is available? But X-rays are like a superimposed image. Coming to CT, it is a slice by slice image. So the first advantage is elimination of superimposed structures. And in CT, it is very easy to differentiate even a small difference in a density of anatomic structure and abnormality. And the images of a CT is of superior quality. And like how we humans have evolved in generation. In CT, it is evolved in generation like us. The first CT, when it was invented was first generation. Here, the number of detector type is 1 and the radiation beam coming from a tube is like a pencil-like X-ray beam. And here both the tube and detector is of translate and rotate motion, and duration of a scan is 5 minutes per slice. And like it has a 180-degree translation for 1 degree rotation between the translation. So for approximately, it will take 45 minutes for even a brain scan. Coming to second generation, here multiple detectors are available. The source is single. Here we have a narrow fan-shaped X-ray beam, and here the tube detector movement is translate and rotate. Here duration of scan is like 5 to 90 seconds per slice, and there is a like 18 translation per 10-degree rotation between the translations. And coming to third generation. Third generation is known as a rotate-rotate type where both tube and detector rotates. Here the detectors are multiple and the duration of a scan is 5 seconds. And these third generation scans are equipped in modern scanners. Coming to fourth generation, it has like 2000, more than 2000 detectors arranged in the outer ring. This is a fixed one which cannot move. So this is a fixed and rotate. Means the tube alone rotates and the detector is fixed. Here also the beam of radiation which we use is wide fan beam X-ray. And the duration of scan is like very few seconds. The only drawback of this is more radiation dose to the patient. Coming to fifth generation, which is a electron beam CT. Electron beam CT is like where no conventional X-ray tube or moving parts are there. It is a stationary, whereas tube is fixed and detector is fixed. It is mainly used for cardiac imaging. Here, electron gun is there, which deflects and focuses a fast-moving electron along a tungsten target ring in the gantry. The detector is also form of a ring permitting simultaneous acquisition of multiple imaging section. Here, the scan time is approximately 0.2 seconds where the whole heart can be scanned. This table is to summarize the all generations of the scanner. Like mostly now, previously I said we are using third generation CT. And we are moving into another technology called slip ring technology. In first or second scanners, when tube is rotated, all cables were connected to the X-ray tube and X-ray tube. But as the advancement came, while for the continuous movement, the cables were the hindrance. To avoid that, slip ring was invented. Like I said, it is an alternative to the cabling system. Slip rings are the electromagnetic devices consisting of circular electrical conductive rings and brushes that transmit electrical energy across the moving interface. And the slip ring design consists of parallel conductive ring concentric to the gantry axis that connect to tune the detectors and control circuits by sliding conductors. This, I said no, these sliding conductor allow the scan frame to continuously rotate with no need to stop between the rotation to rewind the system cable. However, the reduced interscan delay increased thermal demands on the X-ray tube. This resulted in innovation of the helical or spiral CT. Helical CT, this is also known as spiral CT. Here, whatever is the addition, it is like addition of third generation slip ring technology and helical motion, which is known as sixth generation. Helical CT, previously I said, it is also known as spiral CT. As the name itself indicates, there is a continuous rotation of X-ray tube during the table movement. Here, the X-ray tube rotation happens, table movement happens, simultaneously data acquisition occurs at the same time. This coming to multi-detector CT, helical CT has improved over the past few decades with the faster data acquisition and a faster gantry rotation with the powerful X-ray tubes and improved reconstruction algorithm. And multi-detector CT is achieved with the detector system having multiple row of detector elements perpendicular to the detector arc. And coming to MDCT, its higher speed allows the one breath hole scanning with large anatomic coverage, and there are few motion artifacts in situation when a patient has a difficulty to lie down for a long time. And longitudinal coverage can be multiplied by collimator width and pitch and total scan time divided by the gantry rotation time. That's how longitudinal coverage is calculated. And coming to the instrumentation, what are the things available? That is, gantry is there and table is there and control console where we are controlling the system and image reconstruction by how the images are obtained. In gantry, the following items are there in gantry, like X-ray tube and filters. Like X-ray tube of very high heat loading and faster heat dissipation is employed in MDCT. And tube collimator is opened wide along the length of a patient to provide a cone beam geometry. And a special type of filter called bow type filter is used to reduce the dynamic of a signal from the detector. Coming to collimator, it defines the section thickness and reduces the scatter radiation. It is present in both X-ray source and X-ray detector. It is known as pre-collimator. This is known as patient collimator. And coming to detectors, the detectors main help is it can gather the information by measuring the X-ray transmission through the patient and convert the X-ray transmission data into electrical signals. Multiple detector array is the assembly of multiple solid state detector modules. There are two types of detector which is mainly used in CT. One is fixed type detector array and another one is variable detector array, and which is subdivided into hybrid or adaptive. Complete to fixed with the detector, detectors of equal width. Like for example, if it is 1.25 mm of detector size, equal width are stacked in back-to-back Z-axis. To achieve different slice width, the detectors are electronically coupled at beginning of each scan according to the requested slice width. And coming to variable width detector, it combines detector of variable width and at a post-patient collimator to define a slice width. This approach is geometrically efficient because there is less unusable space in a Z-axis. It is like two type where I said it is hybrid and adaptive. Hybrid uses the same width detector everywhere except in the center where only few lesser width detectors are used. Coming to adaptive, narrow detector elements are close to center with and width of a detector row increases at the distance of the center. For example, if it is 1 and like in outer space, it will be like 1.5, 2.5 and 5 mm. In CT, image formation is like first, the X-ray beam passes through the patient and it is detected by the detector and reconstruction is done in computer, and that's what we are seeing as an image. So what it is measuring? Previously I said in the basic, it is measuring linear attenuation coefficient between tube and detector. Attenuation coefficient is a measure of how rapidly X-rays are absorbed within the material. This is how X-ray passes through the patient and enters the detector, and by data acquisition system, we are getting the image. Coming to the data acquisition system, it is a systemic collection of information from the patient to produce a CT image. The CT scan data acquisition is a process of sampling electrical signal and convert the resulting sample. The function of a data acquisition system include measure the transmitted radiation beam, encode measurements to the binary data, and transmits the binary data to the computer. How does it test? It does in the following process where the X-ray photon is received by the detector. And detector detects the intensity of X-ray in form of a current. The current is converted into voltage. An analog signal is converted into a digital form, and this signal can be processed and reconstructed in a computer. This is the simple flow diagram for how it is done. Coming to the image reconstruction. Image reconstruction is mainly done by an algorithm. Like generating an image from acquired data involves the determining the linear coefficient of individual pixels in the image matrix, which is done by various algorithms. These are the some common image reconstruction which are used for CT. One is simple back projection, which is a summation method and merely forms a geometrical construction of an image. And coming to iterative starts with the assumption and compare assumption with the measured value and make corrections and bring into an agreement. In analytical, there are two methods, which is Fourier and filtered back projection. Filtered back projection is commonly used algorithm. It is similar to a back projection, where image is filtered and counterbalance the effect of a sudden density changes which causes blurring. And coming to the last one, DLR. What is a DLR? It's a deep learning reconstruction. It is a newly upcoming thing which is a artificial intelligence. Why do we need a artificial intelligence in the algorithm of a CT? Because it is of high image quality and low radiation dose and fast reconstruction. Here, the DLR algorithm are currently trained prior to installation, making their intelligence static than being dynamically learning system. And Like now Canon and G have recently launched their version of DLR. The one of the main factor in CT, which is like very much useful is like pitch. What is a pitch? Pitch is an important component of a helical scan protocol, and it fundamentally influences following thing like radiation dose to the patient, image quality, and a volume coverage and a scan time. What is a pitch? This is the pitch. Like this is the formula to calculate the pitch. There are like what is a like a table translation in millimeter per a 360-degree gantry rotation divided by a normal slice width. This is there are two types of pitch like beam pitch and a detector pitch. Usually, when we used to advise, we always say the pitch should be more or less equal to 1. Why we are always asking the pitch to be 1? Because there is no overlapping and the scan time is less and less radiation and more interpolation. And these are the other things, whatever happen if pitch is less than 1, it will be overlapping helix and long scan time and high radiation and less interpolation. And if pitch is greater, there is a gap between the helical scan and less scan time but less radiation and more interpolation. And if it is pitches more than 2, it is a large gap between the helix and it's very less time but least radiation and extreme interpolation. But usually we will prefer pitches equal to 1 for all patients. And if it is a pediatric and very not cooperative, we will either go for pitch greater than 1. Coming to the image quality, the narrowest collimation should remain consistent over the coverage of volume and scan time to produce partial volume effect. Fastest rotation time, fastest rotation time to maximize anatomic coverage along x-axis and minimize the motion artifacts. And what the image quality depends upon the following factor like spatial resolution, noise, and contrast. What is spatial resolution? Spatial resolution is like ability to differentiate two objects as a two different points. Coming to artifact, artifact is the distortion or a error in the image that is unrelated to the object being scanned. CT artifact referred to any discrepancy between the Hounsfield unit value in the reconstructed image and true attenuation coefficient of an object. There are many artifacts, but I have covered only little artifact like which is very common. Like first one is a motion artifact, which is due to patient movement result in a image ghosting or blurring. It can be done with proper instruction to patient or using a straps which can reduce the patient movement. And pulsation artifact which is mostly common in aorta. So we'll go for ECG gating. And excess image noise obese patient we use in thick slices. And streak artifact which is from metal or contrast. If it is metal, we'll instruct the patient to remove the object. And if it is a contrast, we'll and it may be caused by contrast. Coming to pitch artifact, this is the star pattern seen of the sharp edges of the vessels. Now the pitch factor should be kept nearer to 1. And another is stair step artifact. Slice thickness must be almost equal to pixel size to eradicate this stair step artifact. And dose modulation in CT, like automatic exposure control is to reduce the patient dose in CT. It can be done in two ways. It can be done either in Z-axis or in Y-axis module. And for CT, there is an automatic exposure control where it automatically modulates the dose according to the scout image based on the thickness of the patient. It is very useful. So it like drastically reduces the dose according to the thickness. If it is a thin patient, it will give according to that thickness, and if it is a obese patient, and the radiation will be generated for that patient. Coming to image rendering techniques. Once I said, like once the CT X-rays are produced, now detectors are reached. After data acquisition, reconstruction is done, and finally image we got. And there are many image rendering techniques so that it can be still enhance the image. Like that, CT images are post-processed in workstation by using different algorithm. One is multiplanar reconstruction, curved planar reconstruction, MIP is maximum intensity projection, and MinIP is minimum intensity production. And coming to 3D images, there are two. One is volume rendering technique and another one is surface rendering technique. Coming to multiplanar reconstruction, in this process, image data are taken from several axial slices and are reformatted into coronal and sagittal or either oblique projection. This is very common and it is done for all scan except brain. And if needed, we will do it in brain also. For that, the scan should be done in helical mode. Next is a curved planar reconstruction. This allows user to designate the central line path around which image is reconstructed. This is demonstrated mainly to see the stenosis of a very tortuous or calcified vessel, and it is applied to non-vascular anatomy also. Like for a kidney, ureter, everything. Ureter is traced for to see ureter calculi and everything. And coming to maximum intensity projection, it is a display voxels of maximum ounce field unit value, each mathematical ray of a reconstruction encounters. It is called maximum intensity projection and it is opposite for MinIP. In MinIP, here the display voxels of minimum ounce field unit of each mathematical ray of a construction is known as MinIP. Here, maximum intensity projection is used for contrast-filled vascular structures, whereas MinIP is used for air-filled structures, like to see cochlea and cochlear bones, everything we use for MinIP. And 3D imaging. 3D imaging, there are two types. I said like a VRT and surface rendering. In surface rendering, it is to display a particular structure of interest, a range of ounce field unit, known as threshold range, corresponding to the particular structure is selected. The voxels with Hounsfield unit values within the threshold range are set to on state, whereas the rest of our voxels are set to off state. This surface rendering image is very well used when they go for a plastic surgery and to design how they need to plan for their surgery, and it is very much useful in cleft lip imaging where they go for surgery. And volume rendering, it is a visualization of a three-dimensional scalar field commonly known as volume rendering. The nature of data is that the surface can be rendered as well as the surface bounding the object. And at last, we come to pros and cons of the multi-detector CT. Coming to the advantage, which is also known as pros, it is substantially shorter acquisition time and considerable reduction of movement artifacts. And it has an increased volume coverage per unit time. And it has an enhanced x-axis spatial resolution, z-axis. And improved 3D rendering with a diminished artifacts. And real-time CT is made possible in this MDCT. And in MDCT, we have seen there is advanced post-processing and it has a greater tube loading and more data generation and processing is possible in MDCT. The cons, every pros has a little bit cons, like it has a high radiation dose compared to all other CT. And there is a data overload because there are too many data which is to be processed and the cost is little bit on heavy side. To conclude, the superior speed of a CT can be used to improve the temporal, spatial and contrast resolution of the images. In addition, CT promise for a clinical applications that were limited by the conventional radiography. As a technologist like we should have a thorough knowledge of a MDCT, which is to handle all problem in any circumstances and for appropriate rectification. Thank you.